So our other method of solving algebraically is going to be elimination method. So we have our steps up above here. First step, which sometimes we'll have to do, not very often. Usually with these it'll already be set up in this form. But basically we'll want to have both our x and y terms on one side of the equation and constant on the other. And then to use elimination method, we'll want it lined up so that we have our x values plus our y values and then equals our constants on one side. So we'll need this kind of lining up because what we're going to end up doing is adding the equations vertically. If necessary, we might need to use multipliers to adjust our equations. So like I showed in the last example with substitution method, we're allowed to multiply across an equation and it doesn't actually change the line itself, it just kind of changes the appearance of a line. So if I have the line, let's say I have something more complicated like 2x plus 3y equals 4. If I multiplied that line by 2, which means I multiply every single term by 2, so if I have the line 4x plus 6y equals 8, those are the same line. So what we can do is use this tool of multiplying. As long as we multiply every single term by the same number, we aren't actually changing our line. At the root of everything, that would be our line. It's just we can change the numbers a little bit so that it helps with the math. So we'll look at cases where we need to do number 2, and then we're going to add the equations together, solve for some variables, and back substitute to solve. So again, just reading the steps, if you haven't done this before, can be hard just reading through the steps, but we'll get some practice with our examples. So, looking at this right here, this is lined up perfectly, and all of these are. We're not going to need to make any adjustments, meaning I have my x values, my y values, the equal signs, and then constants. So what we want to end up doing is we're going to skip over number 2 for this one, and we're just going to go to number 3. And we're allowed to do that with this one. I'll show you in the next one when we need to think about number 2. What we're going to do is add these two equations together. So what this looks like is we're thinking about x plus negative x, and that turns into 0, which is actually exactly what we want to happen. When we do this addition, we want one of our variables to go away so that we can solve for a single variable. So that's perfect. So those just turn into a 0, and I'll write that down, that when you add those together, that makes a 0. Here, with our y values, we have a negative y plus 2y. So that's going to be positive 1y. So what we're doing is just vertically combining our like terms if we're adding these equations together. So that's going to be a positive 1y. And then our equal sign is just going to kind of fall down. And then we're going to add our constants together. So 1 plus 0 is 1. So we want our variables lined up like this so that we can see the like terms and how they'll add together. So with this, we get the statement that y is equal to positive 1. And that right there is half of our coordinate that we're looking for. So with that, we have done step 4. That was solving for our remaining variable since x disappeared. And now what we're going to do is take this value and back substitute into one of the equations. It doesn't matter which one, so that we can solve for x. So let's go with the top equation, x minus y, but now we know that y is equal to 1 equals 1. Add 1 to both sides, and we see x is equal to 2. So we have the solution is x is 2, y is 1. And we're done. This was a very nice example because it was set up for us in a lot of ways, especially with the variable canceling out. which will happen sometimes, but now we'll get into examples where we need to adjust things so that they do cancel. Alright, our next example. So let's say I just went ahead and started adding this together. I'm going to end up erasing this, so if you're taking the notes, you might not want to write this down. You can just listen. If I add these together, so 3x plus 4x is 7x. And negative y plus 4y is a positive 3y. And equals 22 plus 26 is a 48. Then I want to solve, but I'm stuck because we have two variables. And we don't have a way of solving that. In fact, this would graph a line of solutions. Just too many. We should just be getting a coordinate out as the solution to the system of equations. So just adding here didn't work. So this is where we need to think about step 2, where we're going to make an adjustment. And the adjustment is going to come through as by multiplying these equations by a number. And we're just going to need to multiply every single term. So what I want to do is think about like 4x and 3x and multiplying that such that they would cancel out. So something that has to happen, one needs to be positive and one needs to be negative. So with these, I would need to multiply one of them by a negative number, and then one of them would stay positive. Then what I need is for the numerical coefficients to have the same number. So in this case, I would start thinking about like multiplying them up. In this case, I would need to multiply them up to 12s. So they would both be 12. It's just one of them would be negative 12 and positive 12. Anyway, this is getting kind of complicated, so this is where I might go like, well, what's happening with y? Because this has a pretty nice setup. One of them is negative and one of them is positive, so that's an awesome start right there, so I don't need to worry about positives and negatives, so that's taken care of. I have 4 on one of them. All I need is a 4 in front of that y right there. If I have a negative 4y and then plus 4y, those will cancel out. So, what I'm going to do is, just because I want a 4 right there, I am going to multiply this entire equation, again, it has to be every single term, by 4. So what this is going to do, I'm going to rewrite my equation. So multiplying by 4, so now I'll have 16x minus 4y equals 88. This isn't strictly great math notation here, but the idea is that I distribute it to every single term inside that equation. But in the end, these are the same lines because it's just multiplied by a value. And then I'm going to have my second equation, which I'm keeping exactly the same. Now, if I go and add this together, great things are going to happen. So with the x values, 16x plus 3x, so that's 19x. And I have my negative 4y plus 4y, which just turns into a 0, which I'm just not going to write that down then. I have my equal sign, and then 88 plus 26, which is 114. So my y values canceled, which is exactly what I wanted. So it starts with this kind of game of getting positive and negative, and getting same numbers out front. Alright, now I can solve for x, so I'm going to divide both sides by 19. So x is going to be 6. And then with that, I can go and solve for y, and what I'm going to do is plug in x into an original equation. Now, when I back substitute, I like to use the original equations. Just because if any error was made in this process here, this is a spot where we could start kind of checking an error and seeing if anything incorrect happened. So that's just my little thing. Like if I wanted to use this equation to substitute 6 in, I would actually prefer to go with the 4x minus y equals 22. So Let's even do that so that we have that written down in our notes. So 4x, which is 6, minus y equals 22. I'm going to solve for y, so that's 24 minus y equals 22. Subtract 24 from both sides. That's negative y equals negative 2. And then we're just going to divide by a negative 1, which will make that positive 2. Alright, so our solution is 6, 2. And we could check this by plugging in. Again, we'd want to go to the original equations, so plug into both of them and make sure it balances. Or you can look at the graphs and see how they work. Alright, 2 more examples here. So, with these, and I know, 100 times I'll say this for our class, but so many different ways to get to the same answer. So when you're here choosing whether you want the x's to cancel or the y's to cancel, really it's either. As long as you multiply things correctly, it's all good. You'll get to the same solution. So the idea being, like, well, here they have a nice common factor of 4, meaning all I would need to do is multiply the 2 by 2 in order to get the same number. So all that would be required is multiplying one equation by 2, and actually I would want it to be negative 2 because I have this positive 4 and I would need a negative 4 right there. So that's something to think about. Although some students might look at this and be like, ooh, there's our positive and negative, that's taken care of. So then I just need to multiply this by 3 and multiply this by 5. But then you're doing the extra work of multiplying that entire equation by 3, that entire equation by 5. Either way will work. I'm going to focus on canceling the x's. So like I was saying, in order to do that, so I need to multiply this function. If I want a negative 4 as my coefficient for x, I need to multiply by negative 2. So what that's going to look like is my top equation is going to stay the same. 4x plus 5y equals 3. And in the bottom equation, I'm going to distribute that negative 2 so it multiplies with everything. So negative 2 times 2x will be negative 4x. Negative 2 times negative 3y will make a positive 6y. And then negative 2 times 7 is a negative 14. And now, if I go and add my 2 equations together, the x's cancel out, so 4x plus a negative 4x will just turn into 0, which is exactly what we want. 5y plus 6y is 11y. 3 plus a negative 14 is a negative 11. And then we'll go ahead and divide by 11, so y is going to be a negative 1. Then I just need to back substitute so that I can solve for x. Let's use the 4x plus 5y equals 3. Yeah, it doesn't matter which equation you use, so 4x plus 5 times negative 1 equals 3. So 4x plus 5 times a negative 1 would be a negative 5. I'm going to add 5 to both sides. So I have 4x equals 8. Divide by 4. And x is equal to 2. So the solution is 2, negative 1. Alright, just one more example here. So, with this one, looking at our values. So with x, what I'm thinking is, well, they're both positive, so I'm going to need to make one of them negative. I could multiply both of those up to 18 pretty easily, so that's an option. Then I just want to look over at y and see if this is any easier. I would need to make one of them negative, and I could multiply them up to 12 pretty easily, so that's an option too. So it seems like it'll be kind of the same amount of work no matter which ones I do. let's go with, I could flip a coin right now. It really doesn't matter. So let's go with the x values, just so that they're kind of out front. So we'll choose. So to get 18 for both of them, I would need to multiply by 3 in the top function and by 2 in the bottom function. And then what I need to take care of is that one of them needs to be negative. Again, I could flip a coin. Doesn't matter. Let's go ahead and make that a -2 for that lower function. All right, so this first function, I'm going to multiply absolutely everything by 3. So 3 times 6x is 18x. 3 times 4y is 12y. 3 times 10 is 30. And then for the function below, the equation below, multiplying by -2, so -2 times 9x is -18x. -2 times 6y is a -12y, equals -2 times 15, -30. And you might start getting an instinct that something's going to get weird here, and that's exactly what I want us to see. So the x values cancel out and turn into a 0. But so do the y values. So with that, on the left-hand side of the equation, our variables all cancel out, and we're just left with a big 0. When we do this, we do want to see what's happening on the other side of the equation. So 30 minus 30 gives us 0. So what's important here is that our variables disappeared, and we ended up with a true statement. This could all happen and we could end up with a false statement. If we end up with a false statement, that means that there are no solutions, that we're working with parallel lines. In this case, where it's a true statement, this means that there are infinitely many solutions. So let's take a look at the graph of this real quick so that we can see what's going on. So I'm going to graph the original equations as they were given to us. So, in fact, let me delete that other equation. So our first equation, 6x plus 4y equals 10. So there's our first equation. Second equation, 9x plus 6y equals 15. And if you saw that, if I just take away the 5 from the 15, you can see we have a parallel line there with these two. As soon as I type it in as a 15, it overlaps it. So this is a redundant case where the lines overlap and they're intersecting everywhere on this line. So the solutions to this, there are infinitely many solutions, and all of the solutions are along this equation of the line. So that's what happens if your variables disappear. If you end up with a true statement, you're actually graphing the same line on top of itself. If you end up with a false statement, that'd be no solutions because they would be parallel lines.